Good afternoon, everybody, and welcome to the July edition of the Sustainable Futures seminar series. We've got two presenters today who are going to be sharing their research with us. And they are Professor Adrian Ball, MBE, BNFL Chair in Nuclear Energy and Society, and a member of the Dalton Nuclear Institute at the University of Manchester. He's going to be talking to us about how nuclear energy can rebuild its relationship with society. Adrian will be talking to us for 15 minutes, followed by a 10-minute Q&A. So if you've got any questions, do put them in the chat, and I can present them to him. And following Adrian, we've got Dr. Thomas Franklin, who's a postdoc at the Sustainable Materials Hub in the Henry Royce Institute at the University of Manchester. He's going to be talking about post-consumer resin and the circular economy, understanding the quality performance linkage for packaging. And following Tom's presentation, we'll also have Q&A. So once again, do enter your questions in the chat. Without any further ado, I think I'll pass over to Adrian to kick us off. Adrian.
Thank you very much. Let me try and work out how to share my screen and make sure I get the right one, and share sound as well, because we've got a little video. Hopefully you can see my title slide. Somebody's nodding. Excellent. So thank you very much for the invitation to share some thoughts with you this afternoon. I'm going to talk a little bit about how the nuclear industry can rebuild its rather fractured relationship with the world outside the nuclear industry. And as was said, I'm the chair in Nuclear Energy and Society at the Dalton Nuclear Institute here at the University of Manchester. Dalton Institute is the biggest and most wide-ranging research institute in the UK in academia. So we're a key part of the university's research base. Thought I'd say a little bit about me to start with. I'm an engineer by background, but I've spent 40 years in the UK nuclear sector up until last year. The last half of that was in policy, communication and stakeholder engagement roles. So very much the subject of this lecture. And my career was with British Nuclear Fuels, the company that used to run Sellafield up in West Cumbria, and we'll mention Sellafield later on. Westinghouse, a US-based company selling nuclear fuel and reactors across the world, with a base here in the UK, and the UK's National Nuclear Lab, where I was External Relations Director for 10 years. And a couple of years ago, I joined the university as a part-time academic, retired from the nuclear industry last year. So the university is now the focus of my attention. And as it says, my particular focus is on how the nuclear world engages with the wider world outside, whether that be government, whether it's policymakers, local communities, the media, wider public, and so on. And so I'm going to just go back a little bit to the beginnings of the civil nuclear industry, because that's relevant to how the industry engages and where we are today. You'll probably be aware, and it's topical with the Oppenheimer film out at the moment, the civil nuclear industry here in the UK was born out of a national need coming out of the end of the Second World War. We had a program to develop nuclear weapons in the UK, and that led also at the same time to the production of beginnings of civil nuclear power. The civil nuclear program and the military program were hand in hand for a while. And if we go back to that time, the 50s, the 60s, into the 1970s, not just in the world of energy, but more broadly, new technology was seen as key to a brighter future and the great sort of future hopes of a society coming out of the challenges of the Second World War and the difficulties afterwards. Exemplified by the space race and the excitement of getting a man on the moon and the technology that led to that, and almost the feeling that science could get us anywhere and do anything. And the nuclear industry, like many others at that time, that were technology-born industries, some of those new areas coming out of research, the nuclear industry was led by the most eminent scientists and engineers who were leading the real research work. I've shown Lord Hinton, Christopher Hinton, there on the picture, who was one of the pioneers of getting nuclear built in the UK back in the 1950s. So I'm going to start off the session with an early example, not because it's relevant to the way the nuclear industry communicates today, but some of the sort of features of this clip that I'm going to show are relevant. This comes from the 1950s, 1957, in fact. It's a Pathé News report. Now, many of you won't know what a Pathé News report is. Back in the 1950s, most households didn't have a television. And the way that people got their footage of what was going on in the world, their visual news, when they went to the cinema, you get news clips in the way that we get adverts and trailers today alongside the main feature. Back at this time in 1957, there'd just been a fire at the Windscale nuclear plant in Cumbria, the facility we now know as Sellafield on the Cumbrian coast. And that fire had led to a release of quite a lot of radiation across nearby fields. So when you're watching this clip, it's about 90 seconds long. Just remember, this was the entirety of the news that the general public would have had about this particular incident. This wasn't an element in a longer half-hour broadcast or anything else. This was it. And hopefully you will be able to see and hear this 90-second clip called Atomic Milk.
Emergency at Windscale Atom Plant, and the milk from 200 square miles of farmland is condemned as radioactive. But for these filter tops, once nicknamed Cockcroft's Folly because Sir John Cockcroft insisted on them, farms much farther away would have faced not emergency but disaster. Now the worst seems to be over, though Mr. Stan Ritson, who helped to bring Windscale's overheated reactor under control, was radioactive for 4 days and couldn't even kiss his wife till the Geiger counters gave permission. The farmers carry on as usual, for cows have to be milked, whatever happens to the milk afterwards. You can't explain radioactivity to a cow. Milk Marketing Board lorries collect the contaminated milk. The trouble arose when radioactive dust from the overheated pile fell on the Cumberland pastures, and milk samples rushed to Harwell were found to contain 6 times as much radioactive iodine as international health standards permit. So for the time being, down the drain it goes. Meanwhile, emergency supplies from outside are delivered to more than 5,000 people who normally get their milk from the banned farms. Experts believe the danger is already past, but until they're quite sure, the ban stays. With atoms, you can't be too careful.
And probably just worth bearing in mind that final comment. With atoms, you can't be too careful. If you think you might come into contact with any atoms this afternoon, do be extra specially careful. The thing to point out from that clip, oops, beg your pardon, is not just what we learned, but what we didn't learn. I mean, we learned nobody missed out on their morning milk, which is very important, clearly. And we know that Stan Ritson can kiss his wife again after 4 days of being told he can't. But there was no mention of how the fire happened, apart from a passing reference to dust overheating. They never mentioned whether it might happen again. And apart from the fact that some people were prevented from drinking contaminated milk, there was no reference at all to whether anybody's health in West Cumbria might have been affected by the fire and the dust moving across the countryside and the fields. So very much a focus on almost the glib, trivial aspects rather than the kind of thing that people might be concerned about, worried about. And I show that because I think it's perhaps typical in many ways of the way that the nuclear industry has communicated ever since. So we all know nuclear is an emotive word. It's the kind of word when you hear it in conversation, when people overhear something on the bus or the train or in a queue somewhere, you prick your ears up if people talk about nuclear. But what does nuclear mean to you? Is it the Queen opening Calder Hall up in Cumbria, the very first commercial nuclear power station? Is it Sizewell in Suffolk or Sellafield in Cumbria against the blue sky and rolling green fields in the foreground on a sunny day? Or is it protesters? Is it the dangers of nuclear waste? Is it accidents like Chernobyl, nuclear power no thanks, barbed wire fences, security and armed guards? Or actually, is it that? A lot of people in modern culture get their perceptions of nuclear from The Simpsons, because the nuclear industry doesn't give them anything else to think about. And it's alarming the number of people I've shown around plants who actually think that The Simpsons is a semi-serious representation of what the nuclear industry looks like. Some of the headlines that go with that, most of these are relatively old, but they're typical of the kind of thing we've seen more recently in response to things like Fukushima. Nuclear disaster, nuclear nightmares here, nuclear panic, Sellafield and suffering children. So how does the nuclear industry, at this critical time when it's in the news and under the spotlight, respond? Well, quite often, and I put was in the title here, but to some extent would still be relevant. It's too detailed, the communication that comes out. It's loaded with data and references. It's usually full of industry jargon and complex language, often delivered by the wrong people or even the wrong organizations to inspire trust and credibility. It has a history and a tendency to, a bit like in that film clip we saw, address issues that people didn't ask about and ignore the issues that were raised or that people would be genuinely concerned about. And it's almost always too late. Reopening conversations that have ended, often long ended. And I think part of the reason for that is the nuclear industry applies its safety case approach, dotting every I, crossing every T, getting everything double checked by 6 layers of management, all of whom fiddle with it a little bit and make adjustments. It applies that safety case approach to communication. So by the time anything comes out, it's been poured over by multiple layers of an organization, amended 24 times, and the rest of the world has moved on. I'm not going to go through this slide or the next one in any great detail, but these are slides I've used in other material just to show the nuclear industry, like any controversial sector, has an awful lot of audiences that it speaks to, from politicians, local communities, media, partners, potential recruits, itself, the wider energy sector, lots and lots of audiences. And it's got lots and lots of messages. These are all a sample of the kind of topics that the nuclear industry communicates about: safety, security, what's nuclear waste all about, the environmental impact, jobs, supply chain, the technology, and more recently, how much nuclear costs to build, how much it costs to deal with the waste, and the impact or potential impact of nuclear on our energy prices, which is something we're all concerned about. But it's not always very good at matching the topic to the audience. And especially in the past, it's had a tendency to deliver the wrong message, not just at the wrong time, but the wrong message for a particular audience or situation, especially about safety. The nuclear industry is paranoid, not just paranoid about safety, but paranoid about telling everybody how safe it is. It's one thing to be safe, but the more you tell people you're safe, the more you explain it in endless detail with graphs and charts and data, how safe you are, people stop believing you're actually safe. The nuclear industry could easily and perhaps beneficially take a leaf out of the airline industry, where they do the safety briefing quickly while they know you're reading the magazine, and then they get on to telling you whether you're getting fish or chicken with your meal and how nice it's going to be when you get to the other end in terms of the weather. We don't talk about the benefits so much, or they don't talk about the benefits. They more talk about reassuring people on issues we don't necessarily know people are bothered about. But there are genuine concerns. We know people have legitimate and genuine concerns about nuclear and about radiation. It's potentially seen as secretive. The safety and security of nuclear plants is often seen as secretive. People can't hear, smell, or taste radiation. And if they could see it, they wouldn't necessarily know, if there was a higher level of it, how we would protect ourselves. It's complicated technology. It's actually stereotyped along with, rocket science and brain surgery. Nuclear physics is one of those things that is almost comically difficult and complicated and challenging. But we know that when things can go wrong, they go very badly wrong. We've mentioned already the history and the linkage to nuclear weapons. When there are issues, local communities and citizens don't have a lot of control over things going wrong. It's like being a passenger on a plane rather than being the driver in your car. And of course, it leaves a hazardous legacy. We know it does, potentially a hazardous legacy for future generations in terms of the nuclear waste that's produced and managed. And those are all legitimate reasons to be uneasy and wary about nuclear, but the industry's response is far too often along the lines of, don't you worry, we're the experts, nothing to worry about here, lots of data and lots of statistics to persuade you or reassure you, very much echoing the patronizing and glib tone of that film we saw at the beginning. And perhaps even worse, the nuclear industry, particularly when it's talking about new nuclear and the nuclear's role in the energy mix, allows conversations to be framed around the wrong question. It often focuses on the question, should we have nuclear power or not? Should we be building reactors or not? Which is a very binary question, and one it's quite easy for people to respond, well, no, I'd rather not, thank you, rather than thinking, how are we as a society going to meet our 21st century energy needs cleanly, reliably, affordably, and of course, safely? So there's lots that the nuclear industry does badly, but things are, you'll be pleased to hear, getting better. The faces that represent the sector are no longer just the pale male and stale people like me, but they're more diverse than they used to be. Social media is increasingly used as a tool to reach new audiences, sometimes effectively, sometimes less so. It doesn't always reach the places that relevant conversations are taking place, but there's progress being made. And those conversations, especially through the use of things like social media, are becoming much more two-way than they used to be, much less preachy from the industry down to the public, and more engaged and more like a dialogue. But there's still too much emphasis, I think, on safety. There's still a reluctance for the industry to listen before it starts speaking. It wants to get its message across, irrespective of whether people want to hear that and are concerned about that. And it still talks to itself more than it seems to talk to other people. So we might ask the question, why is that important? Well, in relation to nuclear waste, it's very important in the UK, and it's going to be important over the coming years. We've got quite a lot of nuclear waste here in Britain, from 70 years of nuclear energy, and it needs storing securely or disposing of. And the government's policy is to bury that waste underground for eternity in a secure repository known as a geological disposal facility, a GDF. But the key question, of course, where is that going to be? Now, we've had a number of previous attempts to find a suitable location for that repository, and always, due to public opposition, those have failed. Government's approach now is one of explicit volunteerism. And what that means is, before a location can be selected to host this nuclear waste for eternity, that community must explicitly decide and choose that they want it in something called a test of public support. The timing, the nature and the scope of that test doesn't sit with the government. It sits with a community partnership that is largely led by the community itself. And worth noting, no UK infrastructure project has ever been delivered this way before. Usually the government will have a consultation on a new airport or a road or HS2, something like that. They will listen to various views. You can argue how much they might listen to those views. They'll listen to those views, and then they will make a decision, and that decision is where it goes. Not here. The government have almost let go of the steering wheel and said the community themselves have to choose to have this. But if they don't, there won't be one. Timescale for that happening is it's going to be 15 to 20 years before that site is selected through that test. The left-hand side of this diagram shows community partnerships. Those exist at the moment. There's 4 communities already in the frame and having discussions. They're being paid up to £1 million a year to be part of the process. That goes up to £2.5 million a year when people start digging boreholes to investigate the geology in that region. And potentially one of those communities in 15 or 20 years' time will, through that test of public support, decide they want the repository, and then there'll be 100+ years of construction, operation and closure. Cherry Tweed, the former chief scientist of Nuclear Waste Services, the body that's going to deliver that, has put it very succinctly. She said, delivering a successful GDF isn't a technical issue. The technology can all be dealt with. It's a societal problem. It's about the relationship with that potential host community. And there are 4 communities currently engaged in that process. 2 in Copeland in West Cumbria, close to Sellafield, 1 in Allerdale, just north of Copeland, again in West Cumbria. Those 3 all very familiar with the nuclear issue, the nuclear industry, and communities where the previous attempts for siting this repository have been close to. And 1 in Thedlethorpe. You probably won't have heard of Thedlethorpe. It's a disused gas field, gas plant in Lincolnshire. They have no history in Thedlethorpe of anything to do with the nuclear industry before. So the parallel engagement with those 4 communities, 3 of them very nuclear familiar, and 1 of them brand new to nuclear, is going on at the moment. And we will see whether 1 or more of those communities decide that they want to remain in that process through to the end, and ultimately decide they want to host the underneath their community for eternity, where Britain's nuclear waste will live forever. So that was all I was going to say. I could have said a lot more, but I wanted to leave some time for questions as well, and I'm looking forward to those. And I will stop screen sharing at that point if I can.
Thank you, Adrian. That was really interesting. So as we said, if you've got any questions, do put them in the chat. I think one's there just come from Maria. Maria says, "Hi Adrian, thanks for your fascinating and engaging presentation. Is there anything we can learn from other countries, for example, Japan? Is anyone doing GDF well?"
That's a really good question. Nobody has successfully delivered a final permanent resting place for higher level nuclear waste. But in Scandinavia and Finland, in fact, they have a repository, and I think in Sweden, we got to the point, they went through a similar process where there was not just the waste repository, this wasn't a permanent repository, but it was a long-term repository for intermediate nuclear waste that was going to be there for 100 years or so. There were two communities, both of them had had extensive experience with nuclear before, that were down to what you might call the head-to-head final. And one of them was going to receive not just the nuclear waste facility, but also a significant amount of what they call community investment, a large sum of money. And the two, I think it was mayors, the leaders of those two communities, both understood the economic value from nuclear, because they'd had nuclear in their regions before, and they agreed between them that the loser, perhaps in quotes, the loser, the community that didn't get the waste facility, would actually get 75% of the money. So they would both get something. One of them would get the waste facility and a slice of the, you might call, compensation money, but the other would just get 3/4 of the money itself. So they both get something very significant out of that process. It would be great to think that we could end up in that situation in the UK. I wouldn't put my life savings on that, but the Finns and the Scandinavians in general have done it very well, partly by having more perhaps engaging faces, young mothers and people who represent community going out as the faces of the industry and going out early to talk about these things rather than leaving it until the very last minute, until everybody's signed off on messaging, by which time people have largely formed their own views.
Just realised I muted. Thank you for that. Parnian suggests that it's very interesting, but it does still leave the question of safety. So it's still, I'm sure you would agree that safety is still a big concern. Obviously.
Yeah, absolutely. The industry has to be very clear on its safety message, and it has. We know it has all of the data and the statistics and the evidence and the regulatory oversight to reassure people on safety. My point was, don't start by doing that. Start by telling people about the benefits, and then if people have concerns about safety, then you have to have that message there. I was trying to explain this to actually a Japanese minister he was in charge of cleaning up some of the land around Fukushima, and we were having a conversation in a London hotel a few years ago. And I was speaking to him through an interpreter, and he didn't seem to get the message that you can have a very positive message, but the more you hammer it home, it can sometimes be negative. And in the end, I said to him, we're having coffee in the foyer of this hotel. I said, imagine if when the staff had brought the coffee and the biscuits, they'd gone back in the kitchen and brought out the food hygiene certificate and shown us a 5-star food hygiene rating. Would that have reassured you, or would that have made you look twice and wonder why on earth they told you that? Because nobody else does that. No other restaurant shoves their food hygiene certificate down your face along with the menu. They just leave it quietly on the window for you to see it. So sometimes the more you emphasize something, the more it can make people think you're protesting too much.
And that follows into another question, which is how does nuclear industry communications compare with the way other controversial or potentially hazardous activities engage?
I think the nuclear industry has often it's looked at some of the statistics perhaps on its popularity, and I remember somebody once saying that the more the nuclear industry goes out and communicates, the more money it spends on PR, for want of a better term, the less popular it is. I'm not actually sure that that's cause and effect, but I think the nuclear industry has tended to believe that rather. I think the reason is it's spending money at times when it needs to spend money because something has happened and it's almost de facto going to be less popular. I think the nuclear industry could very easily be more proactive, go on the front foot, and go into the conversation that it sometimes shies away from, because it's quite good at going into conversations with other nuclear industry people or other people who it knows are at least neutral or ideally supportive, but it shies away from going and having conversations with people who it knows disagree. And in my view, you can't win an argument unless you're in it. So not taking part in some of those conversations doesn't mean they're going to go your way. It just means they're happening anyway, and you're not getting your voice and your message across. We don't have to win them. Sometimes it's just about making people realize that life isn't as easy and as binary as they might think it is. I used to do talks in the evenings to various groups, and one of them was in Scotland to a Labour Party group, and I knew they were not going to be particularly pro-nuclear, but a lady came up to me afterwards never forget what she said to me. She said, "I don't agree with you, and I'll never agree with you, but I've had a really good evening talking about it." And I thought, what a nice bit of feedback, because we've had those conversations. She doesn't necessarily see herself as ever moving from opposing nuclear, but we've had a good couple of hours where she's listened to both sides of the argument. And I think if that means that that individual maybe, when they're thinking what are the things that agitate them and that they're going to be campaigning against, maybe nuclear isn't quite as high on the list because they can see it's a perhaps a necessary evil in those terms. So much the better.
I think that's quite common to see that in certainly in green circles. People that consider the environment do. I think this is quite a surprise. Well, there's people will assume that everyone who's perhaps on the green side would be opposed to it because of historically they probably were, but because of the kind of context of climate change, it is a lot of Greens, people that are environmentalists do tend to fall in favour of it nowadays, measuring up the pros and cons.
There are even Green. And I hope I'm right in saying this. I think again it's in Finland, but I think the Green Party in Finland may not be the Green Party. Forgive me if I'm libeling somebody, but a group one would expect to be opposed to nuclear has actually come out in favour of nuclear in some parts of the world.
We're towards the end, but we've got a couple more questions. If we can do these two quickly, although they seem quite big ones. Charlie asks, for how long could one GDF continue to store waste in the UK? And how long would it be before it's full? And how long before the ground could be reclaimed?
That's a really good question. The intention is that the how long is essentially forever, in that the waste won't ever be moved from that location once it's been placed in there. And the storage, the grouting of the waste in cement, the storage in stainless steel canisters, the engineered barriers around the facility itself, and all of the measures that would be put in place are designed to last for as long as the waste would be hazardous. So we know that one good thing about nuclear waste is the longer as you leave it on its own doing nothing, it gradually becomes less dangerous because the radioactivity decays away over many thousands of years in some cases. The intention is the waste would stay there forever. The question about when it's full, you have to, at some point, you have to spec the thing and say, right, we're building it that big, which will hold the waste that we have and future waste arisings that we expect to come from a future nuclear program. That's still a little bit of a grey area because we're looking, as you know, at building new nuclear in this country. And so there's a potential that we might find we need a second GDF at some point in our future if we accelerate our nuclear program. But I would say modern nuclear stations produce an awful lot less waste than the ones from the 50s and 60s when the technology was in its infancy and people were not really thinking about minimizing waste and managing waste as part of the plans for nuclear.
So I think we've got 1 minute left in this bit. So we've got another question just come in. So we've got two quick fire questions from Paul Bagley. One is a nuclear accident inevitable and how frequent? And Ruben asks if the main challenge. Oh, if you want to ask Paul's first.
Nobody will ever tell you it's not. It can never happen. It would be brave to think it could never happen. The same way the airline industry won't guarantee you that another airplane won't ever crash. What we do know is safety in the nuclear industry is getting better all the time. The issues that we've seen have been with those stations from the very early stages of nuclear, and we have strong and independent regulation in the UK to make sure that the nuclear industry is as safe as it needs to be, which is much, much safer than virtually everything else that we do.
And then the final one, so pretty sharp past them. Ruben asks, if the main challenge is a social one, to what extent are organisations employing social scientists to solve this issue, rather than focusing on employing scientists and engineers? So it's kind of an interdisciplinary question.
That's a great question, Ruben. If it's the Ruben I think it is, what on earth are you doing dialing in at this time? Because if you're in Japan, it must be very late. But the answer, not enough. We do have at Manchester, final plug perhaps, we do have a network called the BEAM network, which is particularly looking at bringing social scientists in to look at nuclear. Some of those people are people who would not claim to be supporters of the nuclear industry, but look at the way in which the social science underpins the relationships, the sense of place and identity that are formed and impacted by the nuclear industry and its relationship to the communities that it lives in. And it is Ruben in Japan. I've just seen it pop up in the box. So go to bed, Ruben. It's being recorded. You could have watched it in the morning.
Right. Thank you for that. Thank you for those answers, Adrian. That's really good, really useful. And I think we can hand over now to Tom. He's going to give his presentation. Oh, I've got it.
Thank you. Yeah, let me just get my slides up. Hopefully you can all see that. Now let's get me just laser point. Great. Again, thank you for having me. It's a real privilege to speak to you all today. And the overwhelming thrust of my talk will be around waste, plastic waste. What do we do with it? And how can we both minimize the amounts of future waste that we generate and deal with the current, in a sense, backlog of waste that we have. So it'll be quite a technical dive at places into some of the data that we've generated, but hopefully it will be insightful for you all. And just as Steve mentioned, I work in the Royce Institute in the SMI Hub, Sustainable Materials Innovation Hub. And Royce as a whole is focused, as a little tagline there says, looking at advanced materials for a sustainable society. And that's largely across 5 broad but overlapping research themes. I guess I probably fit closest into the circular economy, maybe it's sustainable manufacture a little bit, but overall it's all to do with plastics and also with plastics sustainability as a whole. So plastic waste. The picture on your screen, as you'll see, is just a mound of plastic waste stretching as far as the eye can see. And you'll notice quite a lot of that waste is plastic bottles, which again is the focus of this work. And the real problem is that our current plastics economy is linear. So we extract oil, we make plastic, we make a product, we then use that product, and typically we discard that. Over half of plastics are disposed with no method of recycling or recovering and reusing that plastic. And just to give you some numbers, in the UK alone, in 2021, just over 1.5 million tons of plastic waste were generated. And that is about 9.5 Sydney Opera houses. So an absolutely monumental amount of waste just from the UK alone. That's the waste. In terms of the actual production of plastic, although 6% of the total global oil production doesn't sound like a lot, we're still approaching nearly 400 million tons of carbon dioxide just from production of virgin plastic. That's not factoring in the actual production and transportation costs of those final products. And this all accumulates into quite a significant fraction of the carbon budget. It's projected to be about 15% by 2050. So it's not just the waste itself. It's quite a visual issue. We can see plastic waste, but it's also the invisible, those CO2 emissions, which are also another significant driver. And so the key, I think, if you're going to take just one thing away from what I'm saying, is that the transition to a circular economy in dealing with plastic waste is crucial, where we have a way of taking our plastic waste and bringing it back into that production circle. So we are both reducing the waste, we're reusing that waste and recycling it all. And then consequently, we can extract less oil to make our virgin polymers, and our CO2 emissions also come down as well. So the circular plastics economy is, I say the key. It sounds simple, it's quite a complex issue, but the general thrust is for a circular economy. And so, focusing on the work that I've been involved in as I said, I'm looking at plastic bottles, specifically high density polyethylene bottles. And in the UK, that's about 50% of bottle packaging. So you see this rather shampoo bottle as an example. That is a high density polyethylene bottle. And again, in 2017, this figure is quite old now, approximately 270,000 tons of polyethylene bottles were produced. That figure is obviously much higher now. But of those several thousand tons, 60% typically ends up in landfill or some other form of waste disposal. Only about 40% is collected, and I emphasize collected for recycling, into what we term consumer resin, PCR. And that is typically sorted and washed and collected into these giant, effectively hay bales, plastic bales. Those are then flaked, as you can see here, and then reprocessed back into a polymer. We call it a pellet. You might have heard the word nurdle. That's quite common in the news. And you can see we go from this quite nice, brightly coloured mix, this rather horrible, greedy grey mix of pellets. And the problem is, because you've got a mix of not just colours, but different polymer grades, different consumer uses, so different contamination, you end up with a really variable material that can't really be brought back into the circle to make plastic bottles. The majority of this 40% is typically downgraded, in this case into garden furniture, plastic pipes, those kind of lower value applications. There exists a knowledge gap that relates to the performance of this PCR material, the chemistry to its molecular structure, and that limits the wider use and allowing us to increase the amount that comes back into the production circle, reducing the amount going to landfill, and in an ideal world, sending all of our waste through this PCR cycle and reusing it in a true circular economy. The project itself is very interdisciplinary. There's a chemistry and materials science section, which is the part that I'm involved in. We also have a data scientist working with us, and we're trying to develop structure property relationships between the measurements that we do in the lab and building a data science model that will help us to develop these relationships. We're also working quite closely with our industrial partners. So we are making bottles and subjecting those bottles to typical tests that one would do for a plastic. This is a top loading test. You essentially squash the bottle and see if it leaks or not. Again, we're using those tests to validate this data science model that we're generating. And so the overarching aim is to run a couple of fairly quick tests in the lab, feed those measurements into our data science model, and then ultimately predict how this PCR resin that we have will perform when we make it into a bottle. It may be the case that this particular batch isn't very good. So in a worst case scenario, you would reject that batch of resin, then you're not wasting your production time making a resin that's going to fail. But the hope and the ideal case scenario is that you could intervene at this point. You could add things to your resin, which will be the focus of quite a few slides in this talk. But you can add things to either improve the quality of that resin or tailor the quality to exactly the properties that you want to have. It's quite a novel approach to combining all these different aspects of looking at PCR. And as mentioned, we are heavily underpinned by industry engagement. So Bright Green and Unilever are our major industry partners. And just starting this year is some supply chain work. Again, looking at that whole life cycle, for want of a better word, of production to use to disposal. And again, that is all feeding into this whole picture of the PCR waste flow. So to date, I have to thank my colleague Andy McLaughlin, for all of his work in this. But to date, we've undertaken the largest study of PCR material that is seen in literature. And we're starting right at the chemical level, so really focusing on, for polyethylene, the base chemical structure. We can then move up into our polymer architecture. So as we grow that into polymer chains, how do we characterize that? And then we can move even further into how those chains will aggregate, how they will crystallize, in this case, what the morphology, as it is termed, how that affects behavior. And we can also go right the way up to the bulk properties. So we can look at the melt behavior, we can look at how it processes, and how that impacts the mechanical properties and the bottle properties. So a really broad sweep of different types of characterization, trying to focus on every possible aspect of the PCR. But that does mean we have a lot of data. We have at least 30 different samples, at least 10 different analytical methods. And when you factor in repeat measurements and the number of individual aspects you can pull from each technique, you end up with thousands and thousands of data points. And again, these slides are quite a few years old now. I wouldn't be surprised if this is now double this big on the slide. So it's a vast quantity of data, and trying to sort through that manually is a real challenge, which again is where data science can become such a useful tool. So by using physical component analysis, a more formal definition is down at the bottom here. Essentially, we are reducing the complexity of our data set, but maintaining as much value in that data as possible. So essentially, letting the data itself show us which features are most useful, most important in determining the physical properties and those relationships. And I've said it's those relationships between what we measure and how it performs in the real world, which is the key knowledge gap that we are trying to bridge. And so after you've done a PCA, depending on what techniques you're looking at and what data you're interested in, and depending on how you want to cluster your data, you can end up with plots that are quite similar to this one. So in this case, we're looking at the percentage of polypropylene, which is a major contaminant in polyethylene waste streams, comes from bottle caps, other bottles, all traced right back to when you collect and you sort your waste stream. You want as clean a waste stream as possible, but inevitably some contamination always comes in. And polypropylene has a really detrimental effect on the mechanical properties, so we want to try and minimize that as much as possible. But in this case, we can cluster into 3 different groups. So this light blue one, we have a group of resins that are closest to virgin polyethylene. We have our high polyethylene content cluster here in the yellow. And then our third cluster is resins that are neither close to virgin and neither have a high polypropylene content. They are unique in both of those principal components. So we can kind of take the learning from PCA. We now have different clusterings of resins, and we can start to reprocess that material and characterize what happens as we simulate recycling of these resins. And the way we're doing that is through a process known as extrusion. Excuse me. It's a fairly fundamental process. It forms the basis of pretty much every plastics reprocessing process. You take your solid polymer, in this case pellet, feedstock, and you feed it into a barrel with a rotating screw. And when you apply heat and you apply shear, you melt those polymers, you mix them together, and you can then push them out of the other end through the die at this other end into a filament, which we can then characterize. And the key thing about this form of recycling is termed mechanical recycling. is that it can be quite a harsh process on your polymer. So we've got high temperature, we've got high shear, and we've got oxygen present within this system. And all of that leads to degradation of our polymer chains. So if we start with a polymer chain, it will be quite long, quite entangled. There are broadly two types of degradation that can occur. The first is that we can cut those chains up, they can become shorter, so our material becomes a bit more liquid-like, and we are modifying our chemical structure. The second is that those chains can branch, so they can find other chains and form cross-links or branches to other chains. And so you end up with a much larger network of chains and a more solid-like material, both of which will impact your mechanical properties and how it performs as a bottle. So we want to minimize degradation as much as possible. And it's this question in orange, which is the key to certainly my aspect of the project, is to understand when we do reprocess, when we simulate recycling, what happens to these post-consumer resins? Do they degrade? If they do, to what extent? And how can we stop that degradation? So just to give you a brief overview of what actually happens, we take our polymer chain, shown here, something, whether that be the heat or the shear or the oxygen, will generate what's known as a radical, which is this species here, typically very reactive, and in this case it will react with the polymer chain, and it will take a hydrogen atom and transfer the radical behavior to this chain. So we now have a very, very reactive radical chain, and this is a largely self-propagating reaction. Once you have radicals present, they can be quite hard to contain, quite hard to control. So we get all these different types of reactions, again, all of which change our chemical structure and our physical properties, whether that be through the branching and the chain fission, as we've discussed, but they can also react to make other oxygen species, so a peroxide in this case, which in itself is quite reactive, and so you can get further complex reactions on top of this radical behavior. So it's quite a mix of different factors and different reactions taking place, but what we really want to do is stop this stage. We don't want these radicals to generate and to start these degradation reactions. Ooh, don't know what I've done there. There we go. And one way that we can do that, and it's very common in industry, is to use antioxidants to stop that radical species generation and to really arrest that degradation. And we can broadly split these into two categories. We have primary antioxidants, with rather complex structure. Yeah. The key is actually this hydrogen here on this, it's under a phenolic group. This hydrogen is effectively sacrificed for the greater good of the polymer. So the polymer chain is left untouched, but the additive sacrifices the hydrogen and stops that radical from being generated. But that still leaves you with radical species, less reactive, but can still react and cause damage. They're typically paired with a secondary antioxidant, which again scavenges these remaining radicals and reacts chemically to deactivate this radical into typically an alcohol. But again, we've changed the chemical structure of our additives. So these are sacrificial over time. They deplete, their effectiveness depletes. And so this is more of a bridging solution rather than a permanent solution to stopping that degradation permanently. And as I said, there's the whole field of additives is a real minefield. Different applications, different polymers, different end uses, all can have different additives tailored to them. We had to try and think of a way to cover some of the typical classes, just to try and screen some different additive behavior. And so we've selected 3 different groupings, 6 additives in total. The first 2, the antioxidants that we've discussed just on the last slide. We also have 2 mystery additives, the structures of which we don't know. They are a commercial secret, but they're marketed for bottle production, high density polyethylene bottle production, as a way of helping reduce that degradation. And then these last 2 are known as compatibilizers. So if you remember, I said polypropylene is quite a significant contamination issue. Well, these effectively help to stitch together. You end up with a polypropylene phase and a polyethylene phase. They don't mix, they refuse to mix. So you effectively have compatibilizers kind of acting as a zip. So they stitch those 2 phases together and really help to minimize the effects that polypropylene has on mechanical properties. So 3 broad classes. As I said, this is not an exhaustive list of all the additives possible, but just as a way of kind of scoping out some different possibilities. Our workflow was to take a resin from our principal component analysis and subject that to 5 rounds of extrusion with each of these different additive groupings, and then characterize select extrusion cycles from these groupings with a whole suite of different characterization methods that we have in the lab. And again, you can see the list of the kind of broad information we can get from each technique, some covering the properties, some covering more of the base chemical structure, but all really looking at the effects of degradation on our polymer, both with and without additives, seeing what the effect of these additives is. And I'm going to show some data from these 2 techniques. We could spend hours discussing all the intricacies of the data that we've obtained, which I would enjoy. I don't know if anybody else would enjoy. So I'm going to focus on rheology and tensile testing, just to give you a flavor of some of the challenges that we face when looking at the data and the results that we obtain. So rheology, those who might not know, it's a way of essentially probing the viscosity of our melt as we apply different deformation to it. So how easy is it to move our polymer melt during a particular processing step? But we can go a step further. We can actually look at what's known as the molecular weight. The simplest way to think of that is effectively how long our polymer chains are, in quite a much simplified definition. But effectively, if we have molecular weight changes, we know something is happening to our chemical structure. If the molecular weight decreases, we know that we are getting chain scission, one of those degradation mechanisms we discussed. If we get a molecular weight increase, we're getting chain branching, which is that second degradation mechanism, as discussed. And for polyethylene, branching typically dominates. So if we see an increase in molecular weight, we know we can be fairly confident branching is happening, but we know there's a change on that molecular structural level. So if we just take our resin as it is with no extrusion, we have a molecular weight down here. And if we extrude with no additive, you can see we have a very clear increase in molecular weight as the number of recycling steps increases. So that's with no additive. Both of our antioxidants perform perfectly as expected, nice and flat, very little change in molecular weight. That's what we would expect. So it's arresting that degradation, even in this first and initial step. Our compatibilizers, this is in the grey colour here. Sorry, not the compatibilizers, the 2 mystery ones in the grey and the yellow. Slight increases, but again, nothing as significant as not having an additive. And finally, our compatibilizers show the strangest behaviour. And in particular, this green one here almost mirrors our behaviour when we don't have additives. We know just from this plot Without additives, we're getting branching, we're getting changes to that molecular structure. So we would expect to have a knock-on impact, you know, on our mechanical properties. Some of our additives perform really well, no changes. Others not quite so well, and others really quite poorly. As I've said, what we would expect to see in terms of the bulk mechanical properties is a difference, a change. What that change might be depends on the resin, on the test that we're doing. So we know, as I say, we did some tensile testing, and essentially what we're doing is forming these little dog bone shaped molds and pulling them apart under quite high strain, but pulling those samples apart, and we get quite a lot of different bits of data just from this one test. So the Young's modulus down here is this linear portion, is largely the recoverable deformation. So if you think of a plastic bag, if you were to just gently pull it apart and then release it, it would maintain its original dimensions. If you were to take that plastic bag and keep pulling it, it might be quite hard at first, and there comes a point when it becomes quite easy and you can really stretch it out. That is the yield. So when that polymer yields, that deformation is irreversible. You've changed the dimensions of it. And if you keep pulling, ultimately, that plastic bag or that polymer sample will break. I'm going to focus on the yield and the Young's modulus. Again, just going to go over this quite quickly, just to give you a general overview of some of the data that we've obtained. So, Young's modulus on the left, this is the recoverable deformation. Tensile stress at yield on the right, that's when it yields, when it's irrecoverable. We've changed the shape and the dimensions. And as the colors fade, this indicates increasing extrusion cycles. So the first grouping on the screen is with no additive. And we can see straight away that nothing really happens. We have some very subtle changes. The most significant change is after one reprocessing cycle, but then not a lot happens, which is surprising given the change in molecular weight that we know occurs. So let's look at the additives. Our antioxidants in the red and the blue. In both cases, and for both graphs, we see virtually no change, which again, when we think of the molecular weight, that would fit. We're not changing our molecular weight, so the mechanical properties should stay the same. Our two mystery additives, again, some fairly subtle changes, not necessarily what we would have expected. Typically, one expects, with more extrusion and more degradation, your mechanical properties would decrease. But certainly for this yellow trace, you see we're seeing very subtle increases in our mechanical behavior. Quite strange. And lastly, our compatibilizers, again, quite strange behavior. We know that this green one had quite a significant increase in molecular weight. But again, the impact on the mechanical properties does not appear to translate across. Generally, these overall mechanical properties are lower, which again is surprising. These are compatibilizers. They're designed to at least maintain, if not improve, mechanical performance. So why they would be lower than our resins and our samples with no additive is a mystery, to be quite frank with you. It's a bit unclear. We're still trying to pick apart a lot of this data. So some quite interesting behavior. But to tie everything together, so we looked at kind of principal component analysis as a really useful tool to extract as much data as we can when you have such a vast and complex data set, using PCA to simplify that and to extract the key features and cluster your resins and your data has been a really, really powerful tool. Building upon that, if we look at some of the resins that have been clustered and we extrude them with commercial additives, we subject that to So in this case, 5 extrusion cycles characterize that. We can see that we generate even more data. Some of that data is molecular weight. From rheology, we do see changes in molecular weight, so we know that structural changes, chemically structural changes, are happening to our resins, but that by and large does not translate into mechanical properties. So this could be that polyethylene as a whole is quite resistant to degradation. That despite having changes in molecular weight, despite having changes to your base chemical structure, that doesn't really translate to mechanical properties. It will still perform fairly well in its intended application. In this case, plastic bottles. But yes, it's been a really comprehensive look at PCR. It's been a really interesting project to be involved in. It's also raised a lot more questions in some cases than answers, certainly with our mechanical data. But it's certainly building on our understanding of how PCRs behave and how we can use this to really feed back and really help drive towards the circular economy. And with that, I shall stop there. As I said, this is very interdisciplinary. There are lots and lots of people to thank. They're both here in Manchester and Liverpool, our industrial partners. And I will thank you all for your attention. Thank you.
Thanks, Tom. Really interesting. Obviously, we're in the same group, so I'm quite familiar with the world of plastics now. So we are slightly over time. So we've just got a question from David in the chat. He's talking about milk bottles. So he says that milk bottles' current correct collection rate is 85%, and the current recycled HDPE content in a milk bottle is 30%, approved to 50%. This is segregated material in a closed loop used only in milk bottles. So he suspects the collection rate is lower for toiletries if milk bottles are included in the original data. So he asks if are you able to remove non-food product residue during the cleaning process, and does this affect the recycled HDPE properties? And also, have you engaged with Veolia and Biffa, who currently clean post?
Yeah, so to answer the last question, Veolia and Biffa have supplied some of the resins that we're using. But beyond that, I personally haven't interacted much with them. So our main partners are Unilever and Bright Green, but they have Veolia and Biffa have supplied kilograms of resin to us, which has been very nice. Yes, is the broad answer to the question. Milk bottle collection recycling is typically quite good, and the percentages are quite good. If you segregate your food from non-food, it does become, certainly for the case of milk bottles, easier as long as you're strict with that segregation, to ensure that your material quality remains. Big problem is that you can't take a shampoo bottle, mix it in with your milk bottle waste, and then use that resin to build a milk to produce a milk bottle, purely because of the risk of contamination. There's quite strict limits, quite rightly so, on what resins can be used for food grade and what cannot be used for non-food grade. So yeah, when you start to just pile all your polyethylene in and process it, typically that cannot be used for food grade. If there is a non-food grade source coming into that waste stream as well. If you can keep them separate, then yes, you can process them individually. There's another part of that question, which I'm afraid I've forgotten.
It's suggested that the collection rate might be lower. But yeah, I think David is from Muller, so maybe you could get in contact with you afterwards. And then we are a bit over time, but a quick answer to Rob's question. Rob asks, have you simulated what the maximum number of possible cycles with and without additives would be? Interesting one.
So not for this previous project that some people have been involved in did look at, if you have a bottle, let's say 30% recycled content after 10 reprocessing steps, how much of that is still recycled, assuming you don't add any more recycled content? And after the first 2 or 3 cycles, it does drop off quite significantly. And as far as I'm aware, that work was not factoring any additional additive incorporation. So in terms of this project, no, we've not looked at that yet. It's certainly something we would be very keen to do. As I said, I think there was certainly a white paper from that bit of work. It's a RAP project looking at the life cycle and the lifetime and the amount of recycled resin that comes through with repeated recycling. But yes, it certainly would be a good idea. Certainly something we are very keen to do. And yeah, we'll certainly look to do.
Brilliant. I think Zoe might have done something on that. But anyway, yeah, so thank you again, Tom. And thank you, Adrian. Sorry for running slightly over, but I think it was worth it for really interesting talks and Q&As. And I think we'll be back for the next month for another one of these. So keep an eye out for the email reminding you. And so thank you, everyone. Enjoy the rest of your afternoon. I'll see you in a bit. Thank you. Bye-bye.